Alright, here we will talk about some normal modes of a string. So let me write it down. Some normal modes of a string. Okay, so let's consider a string of length L. So let's consider this is a string of length L, and it is rigidly held at both ends. So its both ends are tied so that it cannot move. It's fixed at both ends, and it's under tension. Such strings are found in many musical instruments, for example in piano, violins, and guitars. So when a guitar string is plucked, a wave is produced in the string. This wave is reflected and re-reflected from the ends of the string, making a standing wave. The standing wave in turn produces a sound wave in the air with a frequency determined by the properties of the string. So earlier we saw that the adjacent nodes are 1/2 wavelength apart. So if we have a situation like this, like a string fixed at both ends, the length L can correspond to lambda over 2. That means it will have, when there's a standing wave created, it will create, let me change color. Okay, that's better. Oops, too thick. This was my fixed end. This is there, and now I just want to change color. So it may oscillate. Fixed end, it may create a standing wave of that kind. Right, let me make it a little thicker. Okay, or it may oscillate equal to change color again. Let's say another situation could be, this is my again fixed end, this is the string. Let me draw a few so that we don't have to change the color. So different situations I'm going to draw. This is again my string length. All right, okay, so L, length of the string, can have a situation like this. This is lambda over 2, or it can oscillate with, these are nodes, so these fixed are there, so it must be nodes, and it can oscillate like this. So we'll create a standing wave like this, or it can oscillate this. It creates like that. So L can correspond to half wavelength, or it can correspond to here 2 half wavelength, or 3 half wavelength, or 4, which is not, I haven't drawn here, so it will keep on doing like so. Or we can write in generic terms, so L, the length of the string, will be n times lambda over 2, and where n can be 1, 2, 3, 4, and so on, all these integer values, right? Yeah, so I can write L is equal to, or maybe I can put suffix ln, will be equal to n L is equal to 2L over n. So this equation gives you all possible values of the wavelength in that string, right? Or we can write Fn is equal to V over lambda n, right? And this Fn is all possible standing wave, resonant frequencies. Okay, so for example, we can say F1 when n is equal to 1, we can say V over lambda 1, right? And or we can write V over lambda 1, and lambda 1 is equal to V over lambda 1 from here is 2L over 1, right? So V over 2L. So this one is called, or this frequency F1 is called fundamental frequency. Okay, or if we use again Fn is equal to V, and lambda n is 2L over n, right? So 2L over n, or n V over 2L, and we know V over 2L was my fundamental frequency, so I can write n F1, right? So where n is equal to 1, 2, 3, just like before, right? The same. So these frequencies Fn are called harmonics, right? And the series you get, and the series is called harmonics. Or harmonic series, called harmonic series. Okay, now there's another name, F2, F3. These are called overtones, are called overtones. So if F2 can be called, so for example, F2 will have two names. F2 can be called second harmonic. So F2 can be called second harmonic or first overtone. Okay, F3 can be called third harmonic or second overtone. So what do you notice? That the overtone is always one number less than the corresponding harmonics. Good. All right.